Subscribe now and press the bell icon. Never miss an update.
In this video I will show you simple analysis of raft foundation, and show you 3 different criteria to avoid excessive punching coming from column load, if foundation is not safe against punching. First, with just increase thickness of raft foundation. Second, with shear reinforcement provide beneath column where excessive punching exists. Third, by providing drop foundation where excessive punching exists. Want to see how to model suspension bridge in SAP 2000? Click on card link showing top right of video. I am using this data for model raft foundation. Taking 4 spans of 25 feet in X and Y direction. There are 24-inch by 24-inch column after each 25 feet span in both direction. I am using FC prime equals 4 ksi and Fy equals 60 ksi. Superimposed dead load on interior column is 400 kip and on exterior column is 200 kip. And live load on interior column is 300 kip and on exterior column is 125 kip. Go to File and click on New Model. Select Design Code to ACI 318-08. Click on Modify/Show for Design Preferences. Go to tab of Min Cover Slab. Input clear cover top and bottom to 3 inch as per ACI code for raft foundation. Click on Grid Only option. I have number of grids in X and Y direction is 5 and grid spacing is 25 feet in both direction. Go to Define. And click on Slab Properties. Click on Add New Property. And defining 24-inch thick raft foundation with FC prime equals 4000 psi. Choose Matte in Type Selection. Uncheck Thick Plate and click on OK. Go to Define and click on Soil Subgrade Properties. Click on Modify Show Property. Defining bearing capacity of 2 TSF. Subgrade modulus equals to 12 into safety factor into bearing capacity. I am taking safety factor equals to 3, which makes 36 into bearing capacity. So subgrade modulus equals to 2 into 2.2046 into 1000 into 36, in which 2.2046 is conversion factor from ton to kip and 1000 is conversion factor from kip to pound. Go to Define and click on Wall Properties. Click on Add New Property. Defining 12-inch retaining wall with FC prime equals 4000 psi. Go to Define and click on Load Patterns. Click on Add Load Pattern. Change name to SDL and load type to Super Dead. Go to Define and click on Mass Source. Dead load, which is self-weight of raft, and SDL, which is superimposed dead coming through superstructure, is mass source. Go to Draw and click on Draw Rectangular Slab/Areas. Go to Draw and click on Draw Points. Drag like this so that all intersection points draw in each intersection point. Points are now visible. These are all column base joints. Superstructure load act on these column joints. Select interior points. Go to Assign Load Data and click on Point Loads. Select Live Load from drop-down list. Input gravity load of 300 kip. Give size of load for punching shear, which is basically column dimension. So input 24 inch dimension in X and Y, which is column size of 24 inch by 24 inch. Go to select and click on Get Previous Selection. Go to Assign. Load Data. And click on Point Loads. This time select SDL load from drop-down list. Input gravity load of 400 kip. Same size of load for punching shear. Select exterior edge points. Go to Assign. Load Data. And click on Point Loads. Input gravity SDL load of 200 kip with 24 inch by 24 inch load size. Go to Select and click on Get Previous Selection. Go to Assign. Load Date and click on Point Loads. This time select Live Load from drop-down list. Input gravity load of 125 kip with 24 inch by 24 inch load size for punching. Go to Draw and click on Draw Walls. Retaining wall is above mat foundation. So select None for wall property below and select 12-inch retaining wall property for wall property above. Similarly, wall height below is 0 feet whereas wall height above is 12 feet. Model wall on exterior edge of mat foundation. See retaining wall has model above mat foundation. Go to Display and click on Show Loads. Select Live Load from drop-down list. Check Show Loading Values. Live Load is now showing in 3D raft foundation model. Select Raft Foundation. Go to Assign. Slab Data. And click on Edge Releases. Check option Vertical Displacement, Shear, and Rotation, Moment, to release from edges. Select Raft Foundation. Go to Assign. Support Data and click on Soil Properties. Select 2TSF Soil to assign on raft foundation. See soil support is showing on raft foundation. Go to Define and click on Load Combinations. Click on Add Default Design Combos. Check options only Strict, Ultimate, and Service Normal. Load combinations auto-generated as per ACI 318 code. This load combo is 1.0 dead load. This load combo is 1.0 dead load plus 1.0 live load, which is service load combination. This load combo is 1.4 dead load. This load combo is 1.2 dead load plus 1.6 live load. Go to Run and click on Run Analysis and Design.
If you want to download CSI Safe V12, click on card link showing top right of video.
For punching check. Go to Display and click on Show Punching Shear Design. Almost all values are more than 1.0, which means raft foundation thickness is not enough to resist punching of column. Right-click on any point to view its detail punching design. Go to Define and click on Slab Properties. Click on Add Copy of Property. Defining 36-inch thick raft foundation. Select Raft Foundation. Go to Assign, Slab Data, and click on Properties. Select 36-inch to assign raft foundation. Go to Run, and click on Run Analysis and Design. Go to Display and click on Punching Shear Design. You can see now all demand capacity ratio are less than 1.0, almost 0.68, which means it's now safe against punching shear. 0.68 is less value of demand capacity. I can little bit decrease thickness of raft foundation. Go to Define and click on Slab Properties. Select 36-inch and click on Modify Show Property. Change thickness to 30-inch. Go to Run and click on Run Analysis and Design. Go to Display and click on Punching Shear Design. Still demand/capacity ratio is less than 1.0 and raft is safe against punching shear. Right-click on any point to see its detail punching design. Want to see how to design steel mezzanine floor in ATABS V19? Click on card link showing top right of video. Select Raft Foundation. Go to Assign Slab Data and click on Properties. Select 24-inch to assign it on raft foundation. As I checked earlier on, 24-inch thick foundation was not safe against punching shear. Go to Run and click on Run Analysis and Design. Go to Display and click on Punching Shear Design. Right-click on point having maximum demand capacity value. This is detail punching shear design. Note down value of effective slab thickness equals 20.25 inch, which is D. Effective punching perimeter equals 177 inch, which is B. Shear force, VU equals 923 kip. I will first check whether I can provide shear reinforcement or not in raft foundation. I have VU equals 923 kip, B equals 177 inch and D equals 20.25 inch from safe results. I can find shear strength of concrete using formulae. 5EC equals phi 4 square root of FC prime into B into D, where phi equals to 0.75 for shear design, and FC prime equals 4000 psi. Input all values in expression, and I get 5EC equals 680 kip. Vn equals 1.5 concrete strength, that is 1.5 into 680 equals 1020 kip. Since Vn is greater than Vu, so I can design shear reinforcement to resist punching shear. Calculate reduced concrete strength, which is 5EC equals phi 2 square root of FC prime into B into D. Input all values in expression and value of 5EC equals to 340 kip. Required shear strength, Vs equals Vu minus 5EC, divide with phi. Input all values and Vs equals 777.3 kip. I am providing all four sides shear reinforcement around column. So Vs over 4 equals 194.3 kip. This is shear force to design shear reinforcement in one side. I am using 4-legged of half-inch dia reinforcement, which has total area of 0.784 inch square. Using spacing formulae for shear, that is S equals AV phi D over Vs. Input all values and spacing equals to 4.9 inch. So providing 2 bars of half-inch diameter having 4-legged shear reinforcement with spacing of 4.5 inch center to center. But I don't know how much length I have to provide shear reinforcement. As know that Vu equals phi Vc equals phi 2 square root of Fc prime into Bo into D. Rearrange expression to B naught equals Vu over phi 2 square root of Fc prime into D. Input all values in equation and B naught equals 480.45 in. As you saw in picture, I have punching perimeter of shear reinforcement equals to 2C1 plus 2C2 plus 4 square root of 2a, where C1 and C2 are x and y dimension of column. Rearrange expression to calculate A equals B naught minus 2C1 minus 2C2, divide with 4 square root of 2. Input all values in expression and A equals to 67.96 in. You saw in figure which I showed, length to provide shear reinforcement is A and D. In this case I am getting 7.5 feet length per side. It means I will provide 2 bars of half-inch diameter shear reinforcement at 4.5 inch center to center up to 7.5 feet length per side. This is detailing of shear reinforcement around column.
For watch complete analysis and design of pedestrian suspension bridge in SAP 2000, click on card link showing top right of video.
Go to Define. Click on Slab Properties. Select 24 inch and click on Modify Show Property. Decreasing slab thickness to 21 inch. Go to Run and click on Run Analysis and Design. Go to Display and click on Punching Shear Design. Right-click on point having maximum demand capacity value. This is Detail Punching Design. Note down value of effective slab thickness equals 17.25 inch, which is D. Effective punching perimeter equals 165 inch, which is B. Shear force, Vu equals 918 kip. I will first check whether I can provide shear reinforcement or not in raft foundation. I have Vu equals 918 kip, B equals 165 inch and D equals 17.25 inch from safe results. Shear strength of concrete, that is 5 EC equals phi 4 square root of Fc prime into B into D, where phi equals to 0.75 for shear design, and Fc prime equals 4000 psi. Input all values in expression, and I get 5 EC equals 540 kip. Vn equals 1.5 concrete strength, that is 1.5 into 540 equals 810 kip. Since Vn is less than Vu, so I cannot provide shear reinforcement to resist punching shear. I have to increase thickness of foundation. Go to Define and click on Slab Properties. Click on Add New Property. Defining drop of 30 inch thick with Fc prime equals 4000 psi. Select type to drop. Uncheck thick plate. Go to Draw, and click on Quick Draw areas around points. Select 30 inch property. I have column to column spacing is 25 feet. So drop dimension at one side from center of column will be L over 6, that is 25 over 6 equals 4.16 feet. Total drop dimension is 4.16 into 2 equals 8.33 feet. I am taking 9 feet drop dimension in both direction. Go to select, Properties. And click on Slab Properties. Select Drop 30 to select Drop Properties. Go to Assign Support Data. And click on Soil Properties. Select 2 TSF Soil to assign soil beneath drop foundation also. Go to Run and click on Run Analysis and Design. Go to Display and click on Punching Shear Design. All demand capacity ratio are less than 1.0, which means drop foundation is safe against punching shear. These are 3 different criteria that how we can counter punching effect in foundation due to excessive loading of superstructure. Judgment from these criteria depend on design engineer to see which criteria is suitable in which situation.
For watch complete analysis and design of raft or mat foundation with drop-in safe V12, click on card link showing top right of video.
If you need any assistance in structural engineering or you want your structures to be designed, you can contact me through given email address. Do like, share and comment below in comment section. Also subscribe and press bell icon so that you will never miss any new video.